So, as a first speaker, I would like, first of all, to thanks the organizer for this organization, for the invitation to this summer school. And I would like to present a project, a work that we are working on with Grasa Carita from the University of Évora and Elvira Zappale from the University of Salerno. And this will be duality approach to polyconvex variational problem. Okay, so the things is that we were inspired by a couple of papers that recently have been published, and actually they developed some kind of duality theory for special polyconvex variational problems. And we look at around, and we know that the duality theory is a very well-known tool in calculus of variation. In particular, it has been very well developed for convex problems. And there have been many attempts to extend the theory of duality in non-convex problems. And there is also a very recent paper, actually, on the comparative tube by Ilaria Fragalai and Guy Bouchité on a kind of generalization in non-convex problem of a duality theory. And there are the two main results of paper that inspired our research. Actually, been published by Wilfried Gangbo and Van der Putten in 2000, and the last one is again by Awi and Wilfried Gangbo in 2014 on arXiv, where basically the main functional that are under consideration are of the following type. So we have a function f, which is a convex function, which depends on the gradient and on the determinant of the gradient of u, minus f dot u dx. And usually, so we consider two domain, omega and lambda in Rd, that will be convex, and a function u that goes from omega to lambda, and let's say determinant of gradient u to be positive, where the function f actually satisfies some growth condition of the following type. So where the function h, which is somehow determining the growth of the function f with respect to the determinant of the gradient, is goes to plus infinity when t goes to 0, and is superlinear when t goes to plus infinity. Okay, so basically, now I'm not very precise in defining where I take the function u, because this will be clear in the sequel, depending on which kind of model we are considering. And the idea is, can we study some properties of a minimizer of functional of this type, studying somehow identifying a dual problem, and see what happened to the minimizers or maximizer of the dual problem. So the aim for this talk is twofold. So the first thing that I would like to do is to review some heuristics in order to understand what is one possible way to guess how a dual problem for the functional I can look like. And the second part, so first we'll do some motivation and heuristics. And this will be actually very useful to understand what are the dual variables in our study. And the second one, actually, we will look at some cases where the duality actually takes effect. So where some cases where we can really establish the duality. Where the duality holds. Okay, so we keep in mind the growth condition on the f with respect to the determinant. These are actually the motivation for considering this kind of functional came from starting from, for example, the Hodgen materials of or solid-like materials when we want to understand or to study the stable configuration of these materials. And in order to give an idea on how one can guess how construct a dual problem for a functional of this type, I would like to start from the classical theory of duality and see what is the procedure that one usually takes on. So this is very, very classical. We know that if we have a functional which is defined like this, so we have a convex function which depends only on the gradient minus f of u dx. We all know that we can identify the dual functional which depends on the dual variable c, which looks something like minus f star of c plus f tilde star of divergence of c dx. Okay, this is the classical way of finding the dual function. So actually, and this is simply because actually we can see the gradient of u as a linear operator, and the divergence is exactly the adjoint operator. So this is the classical duality application of duality. And so in the special case, so let me just for reference see that if f tilde is only represented by the product of a given function, a given vector field f times u, so we can easily identify the so by f star, I just mean the Legendre-Fréchet functional transform in the standard duality. So this is easily identified to be 0 if p plus f is equal to 0 and plus infinity otherwise. So basically, if we want to relate the minimizer of the function, or the functional I, which has this simple form, to the maximizer of the functional J1, the only function phi which really takes some meaning is when actually the divergence of psi is exactly equal to f. So we have the classical duality that we want to basically maximize this function on all the psi such that the divergence of psi is exactly equal to f. This is the classical. So the idea that we want to understand how can work in the polyconvex problem is to see what is the standard and easy relation between the two. Is that how J1 is makes a lower bound for I1, which is just the application of the definition of the differential duality between f and f star. So one simply take the functional I of u, which is given by this, in the case where f is only the product. And here we apply the simple relation of duality between f and its dual function f star. And this gives you directly the bound of this form. Then what you have here is the scalar product between the gradient of u and psi. And then you get minus f dot u dx. So here you can easily recognize basically the j of u. The only thing that one has to do is to apply the divergence theorem here to move the gradient of u on psi that becomes a divergence. Okay, so basically this is minus the integral of f star of z plus we get divergence of psi plus f times u dx. Okay, and in the case where we are interested, when the functional j is different from infinity, actually this thing is 0 because it's nothing but the value of f tilde star. So this is the simple and the immediate relation that one can get to bound from below the functional I of u. Okay, so this is the classical. So what one can think about is say, okay, so imagine now to have not a function which depends on the gradient here, but depends on the determinant of the gradient. So we have something which is not of this type, but a little bit more intricated. So let's see what we can do. And the idea is to start from this functional, which is now can be written in this form. So I get h of determinant of gradient u minus f star u dx. And as before, as we did here, we just want to factorize the dependence on u using some kind of duality out from the functional. And here what we can do is to say, okay, I have h. H will be a convex function. Now I'm just doing some, supposing that I can do all the calculation that I want, then we will specify when we can do it. And so the idea is to exactly apply the same Fenchel, the Legendre transform, but now of the function h. And when we apply the Legendre transform to the function h here, we get a lower bound, which is of the type integral omega. Then we get the h star. Now the h star will be calculated in its variable. Let's call it p by now. And then here we get from the definition p times the determinant of gradient u minus f star u dx. So this term now is actually not immediate to deal with like the one before, because the one before we could use the fact that the gradient u was a linear operator. We'd use basically the divergence operator to move the gradient here as a adjoint, but here we cannot do it explicitly. So what we can think about in order to factorize this term here, actually the idea is that the term that appears here with p times the determinant of grad u is independent on u if p is the composition of a given function with u. So basically we note that if p is a function which is of the form L of u of x, then what we have here in the term which involves the determinant is the integral on omega of L of ux times the determinant of gradient u. And if everything is fine, this is basically the change of variable formula. So this is independent on u, and is only the integral on lambda, where lambda is the image of u of the function L of y dy. So heuristically, oh, sorry. Yeah. Yes, I put the minus in front. Yes. All right. So so this way, if we choose P to be somehow the composition between L and u of x, then this term here is basically independent on u and can be factorized. So the functional became something like h star of minus L of u plus f dot u dx. And then we have this term, which is nothing but the integral of L over lambda. And so now we don't have any more, with this choice of P, this the very bad nonlinear term here in the estimate. And so let me note here what is the kind of duality that we have used. And basically, we have used that h of t plus h star of minus L of u is greater or equal than t times L of u, which is the standard duality with h, just calculated in minus L. So, okay, here this minus. So this inequality here will be used in the definition relation for the dual variable. So the first thing is that doing this calculation, we guess that the function L will be one of the possible dual variables in a functional defined on determinant, so which depends in a convex way on the determinants. Okay, so here now we are in a position where we need somehow to factorize again the u itself from this new strange function, which is now minus the Fenchel conjugate of h calculated in minus L, where L is the first dual variable. And what we do is to apply again a duality relation between two conjugates, but we need to take all this function as a given one. So the idea to define the second dual variable is to say, okay, suppose that k is a function such that when I take the Fenchel conjugate of k, then I got exactly the function that I get here. So minus h star calculated in minus L. Okay. So if I can choose such function k, such that this is true, then basically here what I get is something which is a Fenchel conjugate of a given function k. So I can apply again the standard duality relation. And my functional will be bounded from below by minus integral of, now we have k, where I want to calculate this k. So we look here and we have this function here is just k star calculated in u. Then here with the minus, then here I have f dot u. So what I get is that I can apply duality with both this term and get an f inside here plus the integral over lambda of L dy. Okay? So doing these simple calculations, we have identified a functional now which just depends on k and L. And we factor out the dependence on u. So basically, this thing here will be, it's a candidate to be the dual functional of the functional I2, which is a functional which is h of determinant of u minus f scalar u. And so what we have done, let me just move a little bit this. So, okay. I was hoping that the other one was going up, but it's not. So I just start from scratch again. So the idea is let me just write what are the conditions that we have. conditions on L and K that we have found in order to apply what are the duality that we used and what are the conditions that are on L and K. So the thing is that in the first duality, we applied that h of t plus t times L of u is basically greater or equal than this minus h star of L of u that we have called k star of u. And then we have applied again the duality with k star, which is greater or equal now than minus k of v using the differential duality plus u times v. So if we imagine that we can define L and k as dual variables for our functional, then the defining relation is the following. So we have which depends on h. So it's h of t plus t L of u minus k of v is greater or equal than u dot v. Okay. So this will play an important role, and this is basically the inequality that will define the space of dual variables. So we see that using these heuristics with function that depends only on the determinant, we have found a way of defining the dual variables. And what we will really need, so maybe I can define it just now. So we'll say that the set C of dual variables is nothing but the set of function k and L, such that k is continuous, L is lower semi-continuous, and is equal to plus infinity outside lambda, outside the closure of lambda. So because L has to be calculated in the image of U, and and satisfy the relation that we call it 1 that satisfy 1. Okay. So analyzing this simple functional, we have somehow motivated the definition of this set that we call the set of dual variables. And so the idea, this idea came actually from the paper by Gangebo and van der Putten that actually identified the functional that I just wrote, the J2, in some cases as the dual functional of I1, and using this kind of arguments. Okay, so what happened now if we want to include the dependence on the gradient itself? So we can write the functional in a more general form. Let's start with the simple additive form. So we have a functional which is which depends on the gradient. F and H will be both convex, and we want to see if we can use the same ideas and the same kind of variables in order to identify somehow a candidate of a dual functional for this functional here. The thing is that we can treat the second term here exactly as we did before, using the dual variable k and L that satisfy this. And the only thing that we have to add is to deal with F using another standard duality argument. So what we can do is just to bound by make a lower bound using the F star, which is the Legendre transform of F. We introduce a new variable, which now will be which we call C. And here we get the same term that we get in the standard functional in the convex case. So a divergence of C will come out, plus, again, the same term that we had before. So it's something like h star of minus L of u plus f dot u dx plus, and then we have the strange term that came here, which is nothing but what is coming out using the duality for h. And here we do like before. We consider this function here, we call it just k star, and we factorize the u with f and with the divergence of c, just using the divergence theorem here, in order to find a functional which encode hold the information. So it's this plus now k, since here we have the scalar product with u and f plus divergence of u, we have divergence of c plus f. This is integrated in the x. And then we have the integration on lambda of L dy. And this is dual functional, is the candidate to be the dual functional k, L, and c. And this is basically what you can do when you have so a simple way to do it when you have an additive structure. So the last heuristic things that I will or estimate that I will show is that something very similar can be done when you don't have a structure of sum, so you don't have separated dependence on the gradient u and the determinant of the gradient u, but you have something like what we were looking at the beginning. So the simple thing that one can do, it actually works in many cases, is when when you have the right growth condition on f, is you just subtract h of determinant of grad u and add h of determinant of grad u, and then you have your term minus fu dx. You define this function to be g of grad u determinant of gradient of u, and you do exactly the same thing, but instead of considering the f here, you have to take the differential transform of the function g. But since in this way, using the growth condition, you have somehow separated the dependence on the determinant, you can use the condition on the g star, not in general introducing the new variable depending on the determinant, but just calculating in 0. What I mean is that the kind of duality relation that you use here, you can do it like taking g star and calculate it in c, which is the dual variable related to the gradient, and 0. So if you do this, then you deal with this part here, and what you get from the duality is gradient u times phi, like before, and then the determinant does not come into play here. And so what you get after this differential transform, you get exactly the same term that you get before. So here we can just rewrite what we got, which is k of divergence of c plus f dx plus the integral on lambda of ly dy. Okay, this function here, simply giving a name to this function here, which just depends on psi, and we call it like f star of c, will be our candidate minus j of k, L, and c. Okay, so looking at this simple calculation, what we did was actually to see that a functional which is written in this form, so this J, always satisfy the lower bound with respect to I. And so it could be somehow a candidate to be the dual. Yes?
Just a question. So once you have a J like this, which is a candidate for dual,
Yes.
so what happens afterwards? You have to hope for some other inequality to be true? And
Yes, actually, the thing is that we want to prove that we only have one inequality here, and we actually are doing some heuristics in the sense that we are not specifying where U lives and where psi lives, for example. So now, in the second part, this is just to understand the shape of the possible dual functional, not really the dual function, like the shape, how it should looks like, and how the dual variable should looks like. And then now what I would like to do now is to somehow select some cases, some special classes of function psi, some special classes of function u, or even some modification of the original function I, such that the duality is really satisfied. Because in order to have the duality, we need to know that the infimum of the functional I among a given class is equal to the supremum of the other one. And we hope also to find some information on the minimizer of the first one, looking at the information of the maximizer of the other one. So this first part is just to see how we can guess the shape of some function that could be some kind of dual. And now in the second part of the talk, I will okay, I will not give the proofs, but I will show when the duality really take place, okay? I hope I answered the question. Okay, so good. So okay, so now that we have justified the way that we have justified how the dual function we imagine should look like. Now, I want to analyze one case where the duality really holds, which is a finite dimensional case. Finite dimensional case, which is a little bit in the spirit of finite element approximation. Finite element approximation, and the idea is that we choose the function psi to move in a space S, which is a subset of W1 infinity, a function defined in omega with values in R and the matrix, squared matrix of dimension D, since these are the dual variable related to the gradient. And we suppose that S is finite dimension. Okay, so in this case, we will see that the functional J, defined like this, actually satisfies some good properties of semi-continuity, and there is coercive in some subspace which is like a boundary of C and S, and so we can find basically a minimizer for J, and we imagine that actually this minimizer will be related somehow to some, since here we are minimizing J, this will be a maximizer of minus J, and this will be somehow related to the infimum of a functional I. But what happens is that if here we take a finite dimensional space, then we cannot just take U in a general space like W1P, but we have to enlarge a little bit the set of function U where we can calculate this function. So this motivates the introduction of what is called the generalized modulus of the determinant. Okay, so before doing this, let me just state a very simple property of dual variables. Which is which is the following one. So if we start from the relation 1, which is the one that define the dual variable h and k, so the idea is to find, when we want to find the real duality relation, we want to satisfy the equality. So we want to identify the best way to choose k when we fix L, or to choose L when we fix k. And this is nothing but somehow a generalization of the Fenchel duality. And this leads us to the definition. OK, these are well known. So the L upper sharp operator, I can just write this is the best choice for best choice of k given L, and the k lower sharp operator is the best choice of L given k. Okay, so these two functions are actually convex functions because can be understood as supremum of affine functions or supremum convex, and the idea is that L upper sharp is nothing but so the best way of choosing k is to take k here, you put everything on the other side, and you take the supremum on t and u of u dot v minus t L minus h. So it's kind of defined as the sup. So the nice thing about this this operator is that the functional j is monotone with respect to this operator, in the sense that if we just take j in k L psi for any fixed psi in the W1 infinity or when you want, actually if you move L to k lower sharp or you move k to L upper sharp, then you go down in the value of the functional. So this is always bigger or equal, greater or equal than j of L upper sharp L psi and of j k lower sharp psi. This means that since we are interested in minimizing the functional j, we can always suppose that the minimum, if it exists, is such that it's a couple KL such that k is the L upper sharp, is the best choice for k, and L is the best choice for k, so L is k lower sharp. So this basically leads to the definition of what is called so it's the boundary of the set C, which is the set of dual variables, somehow boundary equal, so it's not really a boundary, but it's only a set of couple k and L belonging to C, such that k is L upper sharp and L is k lower sharp. And we will see if we have time that actually this equality can be characterized via an equation, and this will be useful in improving the duality. Okay, so what we can say as we already said before is that we can minimize the functional j on the set C cross S. So there exists a triple K0, L0, Psi0 that belongs to C dot S, whereas this is the finite dimensional subspace of W1 infinity, such that that minimizes J of K, L, and C on C cross S. Okay, and moreover, we have this relation. So this K L belongs to the boundary of C equal. Okay. So what we want to do is to now understand if this functional J over this space is the dual of is the dual of a functional of this form here somehow. Maybe I can keep this form. Okay. And understand in which space we have to take u. Okay, so what is happening is actually that the functional j is the dual of a new functional which depends on the choice of the finite dimensional space, clearly. So what is this functional? So to define this functional, we need three small things. One is the definition of the absolute value of determinant of grade u. So it's not easy to define the determinant of grade u for a general measurable function, but we can define the absolute value of determinant, just saying that for any u, which is a Borel measurable function, if beta belongs to the det star of grad u, if and only if u pushes forward the weighted measure beta times LD to characteristic function of lambda, where lambda is the convex set image of B, times the Lebesgue measure LD, which just means that beta works like the determinant in the change of variable formula for a continuous and bounded function, like the integral on omega of L of u beta dx is nothing but the integral of lambda of Ly dy. Okay, so this way we have a first object that we need, which is this set that a priori could be bigger than just one element. And one observation that we can make is that the set that star grad u is always a convex set in L1. So this can be useful if we want to minimize on this. And the set of functions us, where we want to minimize now the functional I, will be defined the following way. So we have u defined on omega with values in lambda such that there exists a constant c such that the integral on omega of u times the divergence of c is bounded by c times the norm of c in LQ for any psi in S, where Q is the conjugate of P, for example. Okay. So this set of functions here basically will be the right space when we have to minimize somehow the functional of this form in order to have exactly the dual of the function j on the space C across S. So the thing is that when we move in this space here, u is only measurable a priori, and so we don't have this well defined, but we have this well defined, but this is a set. So we have to somehow modify a little bit the functional I in order to say that we want to project it somehow on S. And so what we need is to define the pseudo projected gradients. And so this can be done since for any u belonging to US. So if we start with a function which is in this space, then there exists a unique pair C0 beta 0 that minimizes the integral on omega of f of, let's say, g times b dx on the set of pairs g and b that are in LP of omega in values in rd times d, so this works like the gradient, times that star of grad u, so u is fixed from the beginning, so this is a convex set in L1, such that they satisfy the relation that the integral omega of u times divergence of c, we can move the divergence using g. Okay, for any psi in S. So this is, I think, pretty standard. We can basically calculate somehow the projection of the gradient and of the determinant of the gradient. And so we call this G0 and beta 0 just the gradient S of u and that S of u. And this will be the projected gradient and the projected that S of gradient of u, the projected modulus of the determinant. And so finally, we can define the functional IS of u, which is nothing but what you expect. So it's the integral of f of grad SU that S grad u minus f dot u dx. Okay? Okay, so these definitions are okay. Once we do that, actually, basically, what we have found is that using the functional J and using the finite dimensional reduction on the space, the finite dimensional subset of W1 infinity as a space where we let the dual variable lives, we find actually that this is the dual of a generalization of the original function that we were looking at, and the function is this one. So basically, what we have is that the functional J on the set C times S is in a duality with this IS. Okay, so how we can let me give an idea on how get the duality in this case. Okay, the thing is, one inequality, the fact that IS is bigger or equal than J, can be obtained actually as we did before. So it's the easy one. The thing is that now we want to start from a triple that lives in C cross S, and we want to see if this function, if this triple maximize minus J or minimize J, then can we recover from this one a couple U and beta 0, so U0 and beta 0 that minimizes this function here. And this actually can be done, and the idea is the following. So we let K0, L0, C0, minimizer of J on C cross S. We know that we can choose this minimizer with a special form. There is a relation between K0 and L0. Actually, these two belong to the boundary C equal. So we have that K0 is nothing but the L0 upper sharp operator, and L0 is nothing but the K0 lower sharp operator. So when we look at what are the equality case in the definition of these operators, we can identify what is the equality case in the what to say, a condition for the equality in the standard, in the easy inequality that IS is greater or equal than J of K, L, C. And in this case, the equality somehow holds if and only if the following equations are satisfied. So U should be, U, which is this one, should be in the subgradient of the function K in the point F plus divergence of C, and L of U plus H prime, or H is the function that gives you the growth of the functional f of beta, should be equal to 0. Okay, so these equality relations actually are used to motivate the choice of U0 and beta 0 starting from the minimizer K0, L0, Psi0 of J. So the idea is that we can use this relation. This is indeed already used by Aoi and Gangbo somehow. And so how to define the candidate to be a minimizer of IS. So you first define a function T0 solving the equation, which is this one. So you basically solve H prime of T0 of B plus L of gradient of K0 calculated in V equal to 0. So you solve this equation in V. So actually this is a little sloppy writing, because gradient of K0, since K0 is only Lipschitz, is not defined everywhere, but here you can take a general measurable selection for the gradient of K0 that always exists. And then you define U0 to be this gradient of K0 or its extension calculated on F plus divergence of Psi0, where Psi0 is the one that gives the minimizer of J, and beta 0 is nothing but P0 of F plus divergence of Psi0. Okay, so what happens is that when one defines, starting from a minimizer of J, these functions here actually, U0 belongs to US, beta 0 belongs to the det star of U0, which defined previously here in that star. And we have the equality that minus J, so maybe I can do this, or maybe I can erase the first one here. So it holds that minus J of K0, L0, C0 is nothing but IS of U0, B0. And so basically, this gives you, since the inequality is always satisfied, this gives you that this J on this set is basically exactly the dual, it's a dual function of IS, where IS is the projection of the function I. So this is in the finite dimensional case. And so how to pass from the finite dimensional case to the infinite dimensional case, there is a way of doing this. And the general to infinite pass to the infinite dimensional case. So the idea is, I think, the classical idea that you can do, and this is standard procedure. So the idea is to define a family of finite dimensional subspaces of W1 infinity, which are defined through a family of triangularization of the domain omega. So let's suppose that omega can be triangularized. And so we have a family of triangularization with the parameter of the triangularization that goes to 0. And for any of these finite dimensional subspace, you can find a functional IS, which will be IS of t. So I will be little, since I don't have much time, I just want to give you the idea of what happens. So the idea is that we will have I of S, let's say Sn or S tau. And we can find for any of these S tau the dual problem. And we expect we can study how the sequence of minimizers of the given functional I of S tau that we have identified using the corresponding dual problems behave, and see if it converges somewhere. So the thing is that this can be done, but the convergence is only a weak convergence in the sense of measures. And what we end up with, also in this case, and actually this was already done in a simplest case, is that the functional that we find where we find the dual is actually a functional which is a relaxation of the original one, which is defined in a space of measure, which are similar to what happens with Young measures. Okay? So with this in mind, let me just write down what are the functional that we have in mind. So Young measure approach. So what we get is, we get gamma. It's a Radon measure. This will be a Radon measure on RD cross R cross again RD cross R cross D, and these are all the variables that are basically the x, the determinant of the gradient of u, the u itself, and the gradient of u. These are corresponding to this one, supported on C, which is nothing but omega times 0 plus infinity. So we have somehow the determinant which is positive, times lambda bar. So the image of u is lambda cross R d cross d, and we define the set big gamma of the function gamma of the measure Radon measure gamma supported in this space, such that the following things are true. So the integral on C of f of ct d gamma is bounded. So the functional f is bounded. Then for any bounded continuous function b, the integral of bx d gamma is nothing but the integral on omega of b x dx, the Lebesgue measure. So this says that gamma, if we saturated all the variables, but this one is actually the Lebesgue measure, then this term here is identified. This term here is identified like a gradient, like a modulus of determinant. So we have L of u times t. The gamma should be equal to integral of lambda of L dy. So here we have that gamma, if we saturate all the variables but t and u, it works like u, gradient of u, determinant of u. And okay, so if we take this function, this set of measures, we can consider the functional I gamma, which is nothing but the integral of C of f, C t minus f of x dot u dx plus, no, okay, this is not dx, sorry. This is the gamma. And gamma depends on, you have x, t, u, and c. So the functional now that generalize our original functional now it's defined in this set of random measure. This is just a way of enlarging a little bit the class. And what happened is that this functional here is exactly, we can find when we let the triangularization goes to 0, we end up with a functional, with finding a minimizer of a functional, which is the dual of this function here. And basically, the dual functional, I just say the shape of the dual functional, which is slightly different of the previous one, of the j, because now we have to set the dual variable psi to be just in LQ. And now the divergence, which before was very easy because we were in W1 infinity, now has to be a random measure. Values in R d cross d. And S could be W1 Q0 of omega R d cross d. And the functional J right here, since now we don't have an easy way to define K of K plus divergence of psi, since divergence of psi is just a measure, we have to add the term depending on the recession function and define J. Now J will be KL of psi. So we have the integral of f star of psi plus with this one term, which before was just the divergence of c plus f. Now, and then integrated with respect to x. And now here we just take the absolute part with respect to the bag of this measure, because now we know that in sigma the divergence of c is only a measure. And we have to add the term which depends on the singular part, which is the support function of the set lambda calculating in the singular part of the divergence of c, which is this measure, plus the integral of lambda of L dy. So we have to add the term that was missing in the functional j, and when we have this, then we have that the functional j is exactly the dual of the functional I bar of gamma in the corresponding space. So we have that when we minimize gamma in the set B gamma, then the minimum here is exactly the supremum of minus j in where k and L lives in the same C, so the same set of dual variables, and psi lives in this sigma of omega. And also in this case, we can prove the existence. Okay, there is the existence of a maximizer here, and there is a way of going back and finding a good gamma here that minimizes the function I. So I think my time's here is ended, so I will stop here, and thank you for your attention. Thanks.